Alright, so let me continue with this discussion about Marty's theorem, okay, which is basically an analog of Montel's theorem, except that you are working with not with analytic functions but with meromorphic functions, okay. So let's look at let's again look at the statement. So you have this domain D in the complex plane, and you have this family script f of meromorphic functions on D. So the script MD is the it is the set of meromorphic functions on D, and mind you, we are considering these as continuous functions from D into the extended complex plane, okay. So you are able to do that because a meromorphic function normally at a point which is a pole it goes to infinity, okay, but then you allow the value infinity and you declare the value at the pole to be infinity, so it becomes continuous. So this set of meromorphic functions is a subset of this set of continuous functions from D to the extended complex plane CU in infinity, which as a metric space given the spherical metric we think of as just the Riemann sphere, okay, with infinity corresponding to the north pole, right. And so you have this family script f of meromorphic functions. You can either use the word collection or family or subset, whichever you prefer, but the point is when is this family compact. So in this case, you know, normally or I should since the word normal is used technically, I should say usually compactness is equivalent to sequential compactness, and then that it means that, you know, saying something is compact is the same as saying that every sequence has a convergent subsequence. So if you want to say that the family script f is sequentially, I mean is compact, you would like to say it's sequentially compact if you want to say it's compact, and then you would like to, which means that, you know, given any sequence of functions in this family, you are able to extract a subsequence which converges. Now what kind of convergence? If we are usually the convergence that we worry about is the is uniform convergence, but of course in the case of analytic functions, the meromorphic functions, you won't get uniform convergence on the whole domain. You will get only uniform convergence on compacta. You will get only uniform convergence on compact subsets, and that's called normal convergence, okay. So in other words, the compactness of the family F is thought of as normal sequential compactness, which means that every sequence in F admits a subsequence that converges uniformly on compact subsets of the domain, okay. So this is what compactness for us means, and Marty's theorem says that this is the same as the family of spherical derivatives of F, namely you take for each small f in script f, you take its spherical derivative f hash of f hash small f hash, and you get this family script f hash. This is the family of spherical derivatives, and that should be normally uniformly bounded, which means that it is uniformly bounded on compact sets. So in some sense boundedness of derivatives is giving you is equivalent to compactness. I mean, if you want to say it in a nutshell, boundedness of derivatives is equivalent to compactness. Okay, and so there are a couple of aspects that I want to stress between this and the original Montel theorem. See, the original Montel theorem was for analytic functions. Okay, so you took, instead of taking a family of meromorphic functions as we have done now, if you had taken analytic functions, okay, then we would have put the condition that the family is uniformly bounded, the family itself is uniformly bounded. Okay, and there the uniform boundedness of the family on compact subsets, that would be equivalent to the family being normally sequentially compact. That is the usual Montel theorem. Okay, and the way we work there is you have the uniform bound. If you restrict to a compact set, you have uniform boundedness of the family. Okay, then from the uniform boundedness of the family you derive equicontinuity, because from the uniform boundedness of the family you get uniform boundedness of the derivatives, and that is because of the fact that the derivatives are expressed in terms of the original functions using the Cauchy integral formula, and you can make an estimation. There are the Cauchy estimates. So the uniform boundedness of the family on a compact subset will give rise to uniform boundedness of the derivatives on a compact subset, and uniform boundedness of the derivatives always gives rise to equicontinuity. So you get, along with uniform boundedness on a compact subset, you get equicontinuity for free if you are looking at analytic functions. Okay, but you see, Marty's theorem is slightly different. What is happening is, whereas in Montel's theorem uniform boundedness on compact subsets of the family is equivalent to the family being normally sequentially compact, in Marty's theorem it is not uniform boundedness on compact, normal uniform boundedness of the family, but it is actually normal uniform boundedness of the spherical derivatives. Okay, so you move from the family, in some sense you move from the boundedness of the family to the boundedness of the derivatives. That is the switch. Okay, and the point is that in a sense this is stronger than the original Montel theorem, because in the original Montel theorem, if you know, if you are looking at a family of analytic functions, and suppose you know that their derivatives are normally uniformly bounded. Suppose I am not given that the family itself is uniformly bounded, but suppose I am given just the derivatives are normally uniformly bounded. Okay, then what happens is, if the usual derivatives are normally uniformly bounded, then it also happens that the spherical derivatives are normally uniformly bounded because of this reason. Okay, because you see, the spherical derivatives are bounded by 2 times the bound for the normal derivatives, the usual derivatives. So if the usual derivatives are bounded, okay, then the spherical derivatives are bounded. So if you take a family of analytic functions on a domain such that the usual derivatives are all uniformly bounded on compact subsets, that is normally uniformly bounded, then also you will get you will get a normal sequential compactness. Okay, because of Marty's theorem. But the only thing is that now you could have because you are considering these as meromorphic functions, you could have the extreme case that all these analytic functions go to infinity. Okay, and by that I mean they go to the function which is infinity on all points of the domain, which is also considered as a continuous function. Okay, and mind you, for that function the spherical derivative is 0, because it is a constant function. Okay, so now what I want to say is, so this is one aspect, that when you move from Montel's theorem to Marty's theorem, you are actually moving from uniform boundedness on compact subsets of the family of functions to the uniform boundedness of the derivatives. Okay, and because you are worrying about meromorphic functions, usual derivatives will not work, for example at poles. So you will have to look at the spherical derivatives. Okay, now that is one aspect. Now here is another important aspect. See, if you know that the Montel's theorem, for example, is actually a deeper version, or is an application of the Arzela-Ascoli theorem. Okay, And what is the philosophy of the original Arzelà-Ascoli theorem? The philosophy is that if you want to say a family of functions is compact, which is the same as saying that it is sequentially compact, namely you want to extract a convergent subsequence from any given sequence, see, you will have to put the conditions of the family being equicontinuous and uniformly bounded. That is why the Arzelà-Ascoli theorem is often referred to as uniform boundedness principle. Okay. So, you need uniform boundedness plus you need equicontinuity together to give you sequential compactness, alright. If you are working with analytic functions, uniform boundedness is enough, okay, because equicontinuity will come out as immediately, it will come out for free because you have the Cauchy integral formula, okay. Now in the case of Marty's theorem, there is a slight advantage. The advantage is that if you see, I have if I look at it in one direction, that is, why is it that the uniform boundedness, normal uniform boundedness of derivatives should give me a normal sequential compactness, okay. What you can guess immediately is that always boundedness of the derivatives gives rise to equicontinuity, okay, it always gives rise to equicontinuity. So, even on a compact set, if you want to extract a convergent subsequence from a given sequence, okay, you would like to apply Arzelà-Ascoli theorem. So, what is missing? What is missing is uniform boundedness, okay, because if you want to apply Arzelà-Ascoli theorem, you need uniform boundedness together with equicontinuity, so that you can extract from any given sequence as convergent subsequence. So, if I restrict to a compact set, if I assume that the derivatives, spherical derivatives are bounded, okay, I can expect only equicontinuity, okay, I will get equicontinuity of the given family of functions, but I do not seem to be getting the uniform boundedness of the family, okay. But here is where the beautiful thing is, you do not need any uniform boundedness. Okay. The reason is because the values are being taken in a compact metric space, okay. See, the values are being taken as far as meromorphic functions are concerned. Where are the values being taken? The values are being taken in the extended complex plane. Extended complex plane, mind you, is identified with the Riemann sphere, and it is a compact metric space, okay. And you know, a compact metric space is of course bounded, it's totally bounded, it's bounded, okay, it's complete, okay. So, there is no unboundedness phenomena that is going to occur in a compact metric space, okay. So, this uniform boundedness condition is not necessary, that is the whole point, okay. So, what I want to say is that your Arzelà-Ascoli theorem, in the Arzelà-Ascoli theorem, okay, we were looking at functions, continuous functions, either real or complex valued on a compact metric space, okay. Now I am saying, and there for sequential compactness of a family of functions, you needed both uniform boundedness and equicontinuity. But if instead of looking at real or complex valued functions, suppose I was looking at functions with values in a compact metric space, okay, that is the change I am making. You try to look at functions defined on a compact metric space and taking values in another compact metric space. The target is not real numbers or complex numbers, but the target is another compact metric space. Then because the target is already compact, this uniform boundedness is not needed. Just equicontinuity is enough and it is equivalent to sequential compactness. That is the whole point, that is the whole point, okay. So what I want to tell you is that when you go to Marty's theorem, okay, you switch to the uniform boundedness of the derivatives and you do not care about the boundedness of the original family of functions locally. That is because now the functions are already taking values in a compact metric space and you do not have to worry about it, okay. So let me explain the proof. Whatever I have circled here is to tell you that what this tells you is that if the family of derivatives of a collection of a family of analytic functions is uniformly bounded, then so is the family of spherical derivatives. So the boundedness of the ordinary derivatives implies boundedness of spherical derivatives. Okay, so that's something that I'm writing here. I think I've cramped it a little bit, so let me get rid of this lemma and rewrite it later. So, oops. Okay, fine. So what I'll do is I'll I'll try to give you the proof of this. So let's go in one direction. So so let me again reiterate, the Arzel-Ascoli theorem is valid, okay, in the sense that sequential compactness is the same as equicontinuity without worrying about uniform boundedness. If you are looking at functions which are taking values in continuous functions with values in a compact metric space, okay, if you replace real and complex numbers by a compact metric space, right, that's the whole point. So just equicontinuity is enough, right, and I'll try to instead of trying to prove a theorem in that generality, I'll even explain to you how you can get the sequential compactness. So what you do is, so let's start this way. Suppose so maybe I'll use, okay, so suppose f hash is normally uniformly bounded. Okay, suppose it is normally uniformly bounded. What do I have to show? I have to show that it is normally sequentially compact. That means you will have to pick up, given any sequence in the family script f, you have to show that there is a convergent subsequence, right? Convergence in the sense of normal convergence, that is convergence on compact subsets. So that's what I have to do. We need to, so let me write that down. We need to show that any sequence f1, f2 and so on admits this sequence in, of course, in I should not say, well, when I put subset, this is, I'm not writing this sequence as a set, okay, because there could be repetitions in the sequence, okay. So this is, by this notation, let me put belongs to, okay. So I mean that f1, f2, etc. is a sequence in f. You have to show that any sequence admits convergent subsequence, and of course it should be a normally convergent subsequence. That is something that converges on compact subsets, okay, uniformly on compacts, and of course on compact subsets the convergence is uniform, right. So uniform convergence. So now, so how do I go about this? So as usual, the moment usually if you have boundedness of the derivatives, the first thing that you do is you get the equicontinuity of the family. Okay, that's always you should remember as a philosophy. Boundedness of the derivatives is a strong condition to imply, that will imply equicontinuity of the original family. So what you do is that, so that's what I'm going to demonstrate. We'll demonstrate that this family script f is equicontinuous. Okay, so we'll show script f is equicontinuous. How do I do that? You check equicontinuity at every point. So what you do is fix z0 in D and a disk, a closed disk centered at z0 in D of sufficiently small radius. So so now you know, so the situation is like this. You have the complex plane, and you have this this domain D, okay, and so this is D. I'm always trying to draw a bounded domain, but it need not be a bounded domain, okay, because if it's an unbounded domain with, I can't show it on a picture. So here is the domain D. It is, the boundary is this dotted line, and what I am having is a point Z0 in D, and I am choosing a sufficiently small disk, such say of radius rho, okay, rho sufficiently small so that the whole closed disk is inside D, okay. The open disk with center Z0 radius rho along with the boundary circle, that is also in D, okay. And what do? I just so I remember that, you know, if you take a function f, small f in script f, mind you, the function is being now thought of as going into the Riemann sphere, okay. So it is going into C union infinity, and the C union infinity is identified, so I put a triple line, okay. This is identified with the Riemann sphere. So what is it? It's just so this is just S2, the real 2 sphere in 3 space, real 3 space, radius 1 centered at the origin. So it's this, you know, it's this thing. So this is the Riemann sphere, and this point corresponds to the north pole, which corresponds to, so this infinity corresponds to the north pole, okay. So your function is taking values on the Riemann sphere. That is how you should think about it, right? And now what is it that I am given? I am given that the family of spherical derivatives is normally uniformly bounded. So that means it is uniformly bounded on compact subsets of D, and this closed disk centered at Z0 radius rho is a compact subset of D. So it's uniformly bounded on that, okay. By hypothesis of normal uniform boundedness of the family script f, there exists an M such that the spherical derivatives of all the spherical derivatives in the family are bounded by M. So let me just put in mod Z minus Z0 less than or equal to. So I have this, okay. This is just the uniform boundedness of the spherical derivatives restricted to this compact subset given by this disk, right. Now what do you do? Mind you that in this situation, since the functions are taking values in the extended complex plane, okay, on the target metric space is the extended complex plane, and the target metric is a spherical metric. That is what you have to remember, okay. The target metric space is the extended complex plane, and on the extended complex plane the metric is the spherical metric. It is actually the spherical distance on the Riemann sphere transported by the homeomorphism of the Riemann sphere with the extended plane, okay. So you should remember, this is the big point to remember. You have to remember that whenever you are working with values in the extended complex plane, okay, in the target space, the extended complex plane, the metric involved is the spherical metric, okay. So if you keep that in mind, this is what is going to happen. You see, if I take 2 points, suppose I take so let me use a different color. Suppose I take 2 points, say Z1 and Z2, okay, inside this closed disk, and I take the straight line segment from Z1 to Z2, okay. Then, and suppose I call this segment as L, okay. Then if I take the image of this segment, the straight line segment under this map f, where f is any function, any meromorphic function in the collection script f, okay, what I am going to get is I am going to get something on the Riemann sphere. I am going to get something, okay. So it is going to be again it is going to be a contour with starting point f of z1 and ending point f of z2. Mind you, now f of z1 and f of z2 are being thought of as points on the in the extended plane, okay. And the image contour, the image contour is going to be just f of L, okay. And what is the if you now you know you can you know that from fz1 to fz2 on the Riemann sphere, that is in the external complex plane, the spherical distance is actually the shortest distance on the sphere. It's just it is the minor arc of the greater circle passing through f of z1 and f of z2 on the sphere, okay. And so what you can write is the distance, the spherical distance between fz1 and fz2, this is certainly it is the shortest distance because it is a geodesic, okay. Curves of shortest length on a surface are called geodesics, okay. In general, if you have a space with a metric, then if you give me 2 points in the space, it's not necessary that the straight line distance, if it makes sense, is the shortest, okay. There could be some other curves depending on the metric, especially you could find the distance along a curve to be smaller than the straight line distance in some cases, for example for spaces with negative curvature, okay. But in any case, if you take a space where a metric is defined and if you take 2 points in the space, then the shortest distance, the curve of shortest distance from this point to that point on the space is called a geodesic, and that is a geodesic distance. On the sphere, the geodesics are all given by the minor arcs of the major circles, okay. So that is the spherical distance, and this is certainly this is the smallest distance, and so this is certainly less than the length, this spherical length. So let me not abbreviate it, spherical length of f of L, okay, certainly, and well, what is the spherical length of f of L? You know how to get the formula for the spherical length. The formula for the if you give me a curve on the plane, that is a contour on the plane, then the length of the contour is just given by integrating mod dz, okay, where z is a variable. You integrate mod dz from the initial point of the contour to the final point of the contour, you get the length of the arc or contour on the plane. But if you want to get the length of the image of the arc, what you will have to do is you have to multiply by the factor which is given by the spherical derivative, okay. If you multiply the ordinary derivative and if it is an analytic function, you will get the length of the image arc in the complex plane itself, okay. That is if you use modulus of the derivative of the analytic function as a scaling factor. But if you use the spherical derivative as scaling factor and you will take the spherical derivative corresponding to a meromorphic function, then you will get the spherical length of the image of this arc on the Riemann sphere, okay. So what is this? This is going to be just integral from z1 to z2 of f hash of z mod dz. This is the spherical length, alright. And what will happen is that, you see, now since you know now the point is that this integration is being carried out from z1 to z2, and of course this integration is over let me put L here because this integration is along the straight line path from z1 to z2, okay, and that path lies inside this closed disk, okay, and on this closed disk all the spherical derivatives are all bounded by M. So you know, mind you, the spherical length is always a non-negative quantity, okay, it's a non-negative real number, okay. So what I will get is that this is certainly less than or equal to M times mod z1 minus z2. This is what I will get, because I can replace this f hash of z by M because M is an upper bound, and the integral from z1 to z2 mod dz is just along the straight line segment, is just the length of that segment, and that's the mod z1 minus z2, okay. So I get this. But now what is the advantage of this? Now it tells me I have got equicontinuity. See, so for epsilon greater than 0, okay, if we choose for epsilon greater than 0, if we choose delta to be epsilon by M, okay, then mod z1 minus z2 less than delta will imply that the spherical distance between fz1 and fz2 is going to be less than epsilon. I will get this inequality. Given epsilon greater than 0, whenever the distance between z1 and z2 is less than delta, I can find a delta such that whenever distance between z1 and z2 is less than delta, the spherical distance between fz1 and fz2 is less than epsilon. And this works for all f in the family script f. so long as Z1 and Z2 lie in that closed disk. So what have I got? I have got equicontinuity. I have got a kind of uniform equicontinuity. You can think of this as either equicontinuity at Z1 or thinking of Z2 as a variable, or you can think of equicontinuity at Z2 thinking of Z1 as a variable. In any case, it is a uniform equicontinuity. Okay. So so what I have got is that f from D f from this disk mod Z minus Z naught less than or equal to rho to the extended complex plane is equicontinuous. And this but then of course I can cover the source domain D, I can cover every point by such a closed disk lying in that domain. Therefore I have got equicontinuity at every point, so this implies that so, and this is equicontinuity for all f in script f. So basically what I am saying is that f is this family script f is equicontinuous on D. So I get equicontinuity, okay, which is what so basically what I have done is I have just shown that boundedness of the spherical derivatives gives me equicontinuity, and that is a very general philosophy. Whenever you have boundedness of the derivative, you integrate and you get equicontinuity. That is a very general thing, alright. Now what I have to show, what do I have to show? I have this, I started with this, I have this sequence here in script f, okay, and I will have to extract a subsequence which converges uniformly on compact subsets. That is what I have to do. What I want to indicate is that you can now do it exactly in the way you proved equicontinuity and uniform boundedness implies sequential compactness in one way of the proof of the Arzela-Ascoli theorem, okay. So what you do is you do so these are the steps, okay. So what you do is we retrace, so oops, we retrace the steps in one way of the proof of the Arzela-Ascoli theorem to extract a normally convergent, so I am using CGT for convergent as an abbreviation, subsequence from the given sequence. Okay. So what do you do? So I'll put it as a star list. So the first thing is find a countable dense subset x1, x2, etc. So you given start with a compact subset K of D, given a compact subset K of D, first find a countable dense subset, okay. Here it's just the general statement that a compact metric space is separable, okay. Then what you do is now you have now go back and think about the proof of the Arzela-Ascoli theorem. What you would do is that you would take the original sequence, you will apply it to x1, okay, and you apply it to x1, you get all these real or complex numbers, okay, and now you will use the fact that the original sequence is uniformly bounded to say that you have a sequence of a bounded sequence, and you will extract a subsequence, okay. Any bounded sequence of real numbers or complex numbers admits a subsequence, a convergent subsequence. That is all you are using. But now you see, look at the present situation. If I apply f1, f2, if I apply this sequence to x1, mind you, let me change the notation to from x1, x2 if you want to z1, z2, because all my points are actually, my compact subset K is actually a point, is a subset of D, and all my points are complex numbers. So let me change it to z1, z2 and so on, okay. Now what I will do is I will apply to z1, I will apply the sequence, okay, and I will get a convergent subsequence. I will get a convergent subsequence. Why is that? That's because if I apply if I apply these functions, I am going to get a sequence of points on the Riemann sphere, which is compact. Therefore, it's sequentially compact. Therefore, every sequence gives me a convergent subsequence. You see, so it works. That's the whole point. So apply the sequence f1, f2 to z1. What will you get? You get f1 of z1, f2 of z1, f3 of z1 on the Riemann sphere. Okay, but this is compact. It's a compact metric space. So it's sequentially compact. And because of that, what I can get, I'll get a subsequence f 1 1, f12, f13 such that f1j of z1 converges. Okay, so this is the key step. Okay, this is the key point of difference. When we were looking at real numbers or complex number, when we were looking at real or complex valued functions, okay, when you applied the sequence to a point, you got a sequence, a real sequence or a complex sequence, but then you extracted a subsequence because you knew it is bounded. And where from did the boundedness come? Okay, it came from the uniform boundedness of the original family. Okay, but now you don't need any uniform boundedness in this case to extract a subsequence, because the values are already being taken in the extended complex plane, which is compact, and it's already sequentially compact. I don't need anything more to extract a convergent subsequence. That's the big difference. Okay, now what you do is, now you iterate. What you do is apply to z2, okay, and you get a subsequence, a further subsequence which is f21, f22, f23 and so on, such that if you take f2j z2, this converges. Okay, and you do this ad infinitum. What you will end up with is that you will end up with this matrix as usual. So you will get this you will get this f, you will get this matrix of functions 1 3 and so on, f21, f22, f23 and so on, f31, f32, f33 and so on. So it goes on like this, and it's the diagonalization trick that we use. What we do is that we extract this diagonal subsequence. Okay, then what is the advantage of this diagonal subsequence? This diagonal subsequence will give you a sequence which will converge at all points of this dense subset, this countable dense subset of K. Okay, so f11, so G1 is equal to f11, G2 equal to f22, G3 equal to f33 and so on, is a subsequence that converges on the countable dense subset Z1, Z2 of K. Okay, all right. And now what you do is, I won't repeat those steps. Now you use we've just now proved that all the functions in this family are equicontinuous. Okay, we have just now proved that. So just use equicontinuity and on this sequence of functions to cook up to show that this sequence is actually Cauchy on the whole space. Okay, and therefore it is convergent. Okay, so so the moral of the story is that at this point you use the equicontinuity of the family, and mind you, that equicontinuity came from the boundedness of the spherical derivatives. That's what you have to remember. Okay, so use the equicontinuity of this so family script f to get to show that G1, G2, etc. is convergent on all of K. Okay, so this is exactly as we did in the proof of the Ascoli theorem. I am not going to repeat it. Okay. Now, so what have we succeeded? Using what we have succeeded is, given any compact subset of D, given a sequence, given any compact subset, I am able to extract a uniformly convergent subsequence. Okay, but then what do I need? I need one. If I change the compact subset, okay, my subsequence could change, but I want one global subsequence which works on every compact subset. And how do you get that? You again get by another diagonalization argument. What you do is you fill up D by a sequence of increasing compact sets, okay, with the property that any compact subset is contained in one set of this sequence, okay, and then use again a diagonalization argument as we use in the proof of Montel's theorem to extract from this a global subsequence which is going to be convergent uniformly on every compact subset, and that finishes the proof in one way of proof of Marty's theorem, that boundedness of spherical derivatives implies the family is normally sequentially compact. Okay, boundedness of the derivatives on compact subsets. Okay, so normal boundedness of the derivatives implies normal sequential compactness. So let me write that very quickly. As in the proof of Montel's theorem, fill out D by an increasing sequence of compact subsets and use a diagonalization argument to extract a global subsequence that converges uniformly on every compact subset of T. So this proves one way. What is the other way? You have to show that if you have a normal family, you will have to show that it is the spherical derivatives are bounded, and the other way is proved by contradiction. If the spherical derivatives are not bounded, okay, then I can extract a sequence. I can find a compact set and a sequence of functions and a sequence of points at which the spherical derivatives are becoming bigger and bigger and bigger. Okay, now from this sequence of functions, because I assume normal sequential compactness, I can also get a subsequence which converges. Okay, if the functions, if a family of functions meromorphic functions converges to a limit function, then the family of spherical derivatives will also converge. Okay, but mind you, the spherical derivative of any function is always a finite quantity. The spherical derivative of any function, meromorphic function, is only a finite quantity. Even if you take the function which is uniformly infinity, spherical derivative is 0. Okay, you will only get a finite quantity. So if the sequence of functions converges to a function, then the sequence of spherical derivatives converges to the spherical derivative of the limit function, and that is a finite quantity. But on the other hand, the original sequence had points where the values were becoming larger and larger, so that is a contradiction. So that contradiction will prove that, if you assume that the family is normally sequentially compact, the spherical derivatives have to be normally uniformly bounded. That is the other way of the proof of Marty's theorem. Okay, and with that we are through with the proof of Marty's theorem, right.